As I mentioned in class, physics is the scientific study of how things move and how their movement changes, why things move and why their movement changes, how objects interact with one another, and we start our semester with how objects move, which is sometimes called kinematics. Here we see this toy buggy moving across the screen. We know how to make measurements to describe its motion. As it moves across the screen, how far does it go? How many times a meter stick's length does it move across your screen, and in how much time? I placed this yellow tape measure on the screen, or rather on the track, and we can measure on the screen here that this is 10 centimeters from red mark to red mark, so that's another 10 and another 10, and so from here to here is a total of 50 centimeters, or half of a meter. We measure how far the toy buggy goes by comparing it to that tape measure or a ruler. Once I know the distance that the buggy has traveled, I went in to the computer and opened up this software called LoggerPro, and I went frame by frame through the video and made a data table that you can see on the left side of the screen here, marking where the buggy is and what time it is in the video. If we were in person, we would make a data table and a graph on a whiteboard or chalkboard, and it would look a lot like this. Notice that on the graph here I have a series of blue dots and a series of red dots. That's because every point on the video screen had both an X location and a Y location. My screen has these two dimensions, and they've all been marked in my data table an X and a Y location. What's happening in the X direction, as you look down the data table or at the red dots on the graph, you can see that for every small amount of time that elapses, the buggy has changed its location a small amount in the X direction. That collection of data points, when looked at collectively on a graph, looks like a linear relationship between the X location of the vehicle and the time. What's happening in the Y direction, if I look down the data table, it looks like not much is happening. And if I look at the graph, it looks like not much is changing in the Y direction as a function of time, which does match what we saw in the video. The buggy moved from left to right across the screen, and it didn't move up or down on the screen. We do need to keep track of whether things are moving in the X or Y or Z dimensions. If the motion of an object is only in one dimension of space, we only need to worry about graphing and working calculations in that one dimension. We would usually just call that dimension X. So we would talk about the buggy's position as a function of time. Its position X as a function of time. The linear relationship that graph shows me makes me think that it would be a good idea to get a line of best fit on my graph. So I tell my software to show me a line of best fit. It tells me here on the small box, I don't know if you can read that, but it says there's a linear fit for the video analysis, and it's giving me an equation in the format of y equals mx plus b, which is the familiar general math format for any linear function. However, y equals mx plus b is a very general mathematical format. We would like to make sure that the y and the x in that equation are not being used as y and x the way mathematicians do. Rather, convert them into something that makes sense to us as physicists, where x and y and z all mean something spatial. So what is an independent variable here? It's not x, it's time. Time is what's on my horizontal axis. What is my dependent variable is the position of the vehicle, which is going to show up on the vertical axis even though we are calling it motion in the x direction. So rather than referring to these as the x and y axes, we may want to refer to them as the time and x axes. That sometimes takes some getting used to, referring to the vertical axis as an x axis. If that's confusing, then don't do that. Call it a position axes, and that's just fine. The computer tells me that the equation of this graph is x equals mt plus b, where m, just like in algebra, is still the slope of my line, and it's telling me my slope is 0.1586 meters per second. So there are units in my slope, and we'll come back to that. It says that b, the intercept, is negative 0.06157 meters. approximately 0 meters. We'll talk about what the intercept means too. Well, why would I want to take a data table and make a graph out of this? This is science, so we're doing this in order to make predictions. What can be predicted based on the graph and the equation that we have here? A good prediction would be something like this. Where will the cart be at 3.610 seconds into the video, just based on the information that we have in the data table and the graph? I would want to calculate where it is in the x direction using the equation that we just got right off of that graph. The y equals mx plus b format said x equals m, which is the slope of the graph, times time, plus the intercept of the graph. I don't need to use m and b from the y equals mx plus b format. I don't need to ever call that m or b here. Those are, like I said earlier, general mathematical descriptions. Here we can just call it the slope of the graph and the intercept, and that's sometimes much more clear. The position in the x direction for that cart is the slope of the graph times time plus the intercept. The slope of the graph was, according to my graphing software, 0.1586 meters per second. The time that I'm being asked about is 3.610 seconds into the recording, and the intercept is approximately 0, so it's not going to change it too much. We would calculate the position in the x direction, and I get that in the x direction the cart should be at 0.51097 meters. Of course, I'm going to round that off a little bit. We're not going to get too picky about significant figures in this class, but they do still matter. If I wanted to calculate where it is in the y direction, I would point out that our y direction was not very interesting. We didn't think the cart was moving at all. And so the y direction, meaning how high it is on the screen, the cart would be expected to still be at the 0.05 meters that it was initially. That's our answer, and we can check it by going back to the video. And specifically, when we go to the video, will we see that at 3.610 seconds, our prediction is accurate and the cart is actually at x equals 0.51 meters, y equals 0.05 meters. And so I advanced the video and took more data, and I found that at 3.61 seconds, the cart is at x equals 0.5177 meters, which matches what I had calculated, 0.51 meters, to within rounding. If we were to zoom in and check on the data table, we would see at 3.610 seconds, our x position and our y position were correct to within rounding, which means that this was useful to us as scientists. Again, that's the whole point in trying to, when an object is in motion, its position is changing as time elapses, and that relationship between the change in position and the change in time can be given in the slope of that graph. That is the whole point of what we're doing here. The intercept of this graph gives us information about the initial condition, but the slope tells us something about how the position changes over time. So a good question for you before the next video would be, what would a steeper slope mean? If this graph had been steeper, what would that mean was happening on the video?